people can hear me. Yes, I say thumbs up. Thank you for joining me. My name is Geir Eide. I head up one of the product management teams at Siemens EDA, the Tessen team at Siemens EDA, if I can, always hard to get going after lunch. So for those of you not completely familiar with us, so Siemens EDA provides software and hardware for design of integrated circuits and electronic systems. We have customers and users designing anything from tiny analog circuits to the biggest server systems out there. We're involved in RISC-V through, we're a member, we're an active participant in several of the working groups. And we also have customers obviously designing different types of RISC-V-based systems. And I'm sure you've seen tons of slides like this where people are trying to tell you what your problems are. But if you kind of look at the different challenges associated with RISC-V designs, one way to look at it is that it really comes in two separate categories, right? It's challenges related to the RISC-V architecture itself and where it stands. And you see examples of that on kind of the right and left sides, outermost sides of the slide, right, where the flexibility of the architecture and also where we're at with the ecosystem, how that's still evolving, means that it kind of increases the burden on the of the integrator. Right now, obviously, things are improving pretty much by the minute. Now, the other category of challenges has more to do where the industry is at, right, and what types of chips that we are designing this day and age. And what I mean by that is that when x86 came along, we were in the PC era. When ARM came along, we were in the mobile era. And when RISC-V came along and is kind of gaining a lot of traction, we're in the AI era, right? So a lot of the challenges we see associated with RISC-V designs have to do with the types of designs we're developing today, which are largely software-driven designs that are tuned to work with a very sophisticated, complex software workload, designs that are inherently very complex. It's not, when we talk about a RISC-V SoC, it's not just a RISC-V core and some memory behind it. It's like a monster of a design with hundreds of cores, different accelerator, and so forth. So dealing with that class of designs is something we see very often in context of RISC-V. Now, so I'm going to cherry pick a little bit, if you will, some of the things we're doing at Siemens related to trying to address some of these challenges. So it's going to be a few samples based on the technology that we're showcasing here, and that you can also come visit us in the booth and talk more about. And these are things that relate to IC design, IC verification, and post-silicon debug and software optimization. So we'll start with the design side, and a lot of SoCs today leverage accelerators in some way, shape, or form. And the purpose of an accelerator, or what an accelerator is basically a hardware implementation of something you, in theory, could have also implemented using general purpose hardware and software. And the motivation behind going the accelerator route is that you end up with something that has significantly higher performance and uses significantly less power. Now, you'll find accelerators represented to perform lots of different tasks across many different applications. But of course, the downside is designing hardware is hard, right? And it takes much more effort. Once you've settled on an implementation, you're stuck, right? You can't just go in and change the code. And that's where high-level synthesis comes in, right? So high-level synthesis, the idea is to provide an automated path from C++ to synthesizable RTL, and basically accelerate the path from algorithm to chip. This high-level description could be an algorithmic description of what you're implementing. It could be an embedded software function running on embedded CPU, such as a RISC-V code, for instance. And this, again, could be implemented as and deployed as a coprocessor or a bus-based accelerator as part of a bigger system. And again, the main motivation here, right, is to make it easier to develop things like an accelerator, and also to address some of the otherwise disadvantages of going that route. So for instance, this allows you to do a lot of exploration, right? Testing different algorithms and different architectures before you settle on what is the best, again, because this is a relatively fast and automated approach. It also speeds up the verification process itself. It's faster to simulate C++ than it is to simulate RTL. And again, addresses the time to market, not just for the initial design, but also for derivatives, because now the source code is C++ and not something that's more hardware specific. It allows us to do what our managers tell us to do all the time, which is do more with less. Again, because you rely less on design IC, design expertise. And it also sets you up for reuse, again, in the sense that the source code here can be retargeted many different types of hardware implementations. So that's a little bit about high-level synthesis. Then there's actually a workshop later today, hands-on workshop down on the floor, where that will take you through implementing a RISC-V coprocessor using high-level synthesis. I have the details towards the end. But let's move on a little bit and talk about verification. And as we talked about earlier, part of the interesting bits of RISC-V is the configurability, customization options related to the RISC-V cores, and that of course creates sometimes a bit of a verification challenge. That's where Questa processor comes in, and this is something that's part of the Questa 1 family of AI-powered verification solutions. Questa processor is a formal verification-based approach to basically ensure that your processor is compliant with the instruction set architecture and the prerequisites. This helps you speed up the overall process. You don't have to write the test bench. You are able to find RTL issues earlier in the flow. It's automated in the sense that you don't need to write the functional coverage model. It's designed for custom extensions and extracting the microarchitecture. And we're also demonstrated that it is exhaustive. We have published a few different case studies from both core implementers and core integrators that has documented we've been able to find bugs this way that otherwise would not have been found. Now, once you're satisfied with your core and you move on to building your big, beautiful SoC, you might need some extra horsepower to validate the entire system. And that's where the Veloce platform and family of prototyping and emulation platform comes in. This has now grown to be a family of multiple different products with slightly different purposes. Veloce Strato CS is the emulation platform. It's simplified. The problem it addresses is making sure you get the hardware right. It's built to give you a lot of insight and visibility into emulating the hardware design itself. It can tackle designs up to 40 billion gates. Kind of moving on to now getting your firmware and your software right. The Veloce Primo platform is an enterprise prototyping platform that allows you to deal with early software bring up and accelerate that bit. Whereas moving on to your benchtop is the Veloce Pro FPGA platform, which is a smaller kind of individual prototyping platform that is the kind of lowest cost per gate in the overall platform. Now, the secret sauce, though, in this platform isn't necessarily just the box, it's the hardware itself. It's the solutions and applications that are built on top of it. So, for instance, to be able to validate, again, not just the SoC design itself, but how it operates in the system, we have a range of interface solutions, for instance, PCI Express, virtual 5G, that allows you to verify how your system actually interfaces with other applications in the real world where it will be deployed. Moving on to the hardware-software integration, CodeLink allows for hardware-software code verification by allowing you to debug the embedded software, like in context of that specific circuit. It allows you to. It's integrated with visualization environment. You can trace software executions at breakpoints to kind of do full software debug prior to your design being finalized. For firmware development, Veloce vProbe is a kind of virtual JTAG environment, so you're able to basically validate your debug interface, your debug environment on the emulator prior to silicon. And last but not least, the Nexus allows you to shift the whole software development process left, meaning that so you can start software development using a virtual or a hybrid model. So again, before your entire design is processed or is frozen, you can kind of replace the RTL block of your design with a model and start that development process early. So now that you're confident that your entire design works, it will tackle your software. Silicon comes back, and now your emphasis is on, making sure that my software actually works, and it works the way it's supposed to be. And that's where test and ultrasight comes in. So test and ultrasight is based on a set of functional monitors that are deployed in your design. I'll talk a little bit more about that, but the purpose of these monitors is to give you some extra sets of eyes to see what's happening inside a chip, inside the silicon, when the software is running on it. Now, these monitors are smart and configurable and can also cross-trigger each other, so that, for instance, based on a particular measurement in one monitor, it will automatically trigger measurements on a different monitor. And all of this data generated by these monitors can be accessed and analyzed through a flexible software interface based on whether you're doing debug in the lab or whether you're kind of continuously monitoring the behavior of your software when the system is deployed. And along with this is lots of different bits and pieces to make this a complete ecosystem with automating the generation of these monitors, as well as verification and make the ability to make sure that you can access these through many different types of interfaces, whether it's external or internal interfaces. Now, as I said, the core to test and ultrasight is a set of embedded monitors, functional monitors, that each of these different types of monitors can observe different parts of your design, and whether it is to observe what's happening around the processor cores themselves or across different components of the design. We have, especially in context of RISC-V, we have modules that are there for run control and e-trace trace encoder. But there are more generic purpose instruments like the status monitor, which is basically an embedded logic analyzer, and then instrumentation that allows you to do logging and interface with the system, kind of like giving you like an UART-like type of interface. So this is very flexible and configurable, but again, part of the solution here is the automation that allows you to configure this right for your design. And to make all of this useful, once you have these instrumentation in your chip, and you have the infrastructure to go along with it, it can be accessed in, through different use models, like as part of your initial benchtop lab debug. We have the ability to use your favorite IDE and connect that through our host suite platform to access the instrument and leverage the instrumentation. You can also build your own applications if you have specific requirements through the API, so that's part of that system. And that can also be extended to automated monitoring. Again, you can build applications using our SDKs to automate, do continuous monitoring when a system is deployed in the field, whether it's continuously or for remote debug. And last but not least, we are working with partners such as Louderbox so that the debuggers that you're already using can leverage the type of instrumentation, the instrumentation from Ultrasight. So in a nutshell, that's what I had to share with you. I give you a little sampler plate, if you will, of what we're doing at Siemens EDA related to RISC-V type designs. We talked a little bit about designing accelerators, verifying processors, verifying, validating SoCs, and doing debug and performance analysis. Welcome you to come by our booth, but if you don't want to talk to like marketing people like myself, check out some of the technical sessions that we're a part of. The first thing that's happening in about half an hour is the hands-on workshop that I talked about. We'll also see, there's also a poster that talks more about in-field monitoring and using trace as part of in-field monitoring. And last but not least, a demo of the last product we talked about happening on the floor, I guess just before there's free alcohol on the floor later today. So thank you very much for your time.